So in the last few lectures, we talked about primarily hyperbolic problems of second order and parabolic problems. And so these are time-dependent problems, and there are very specific techniques with which you attack them. So for hyperbolic problems, you would typically use an explicit time-stepping method. For parabolic problems, you would typically use an implicit time-stepping method. Now, when I introduced to you a taxonomy of time-dependent problems, there was a third class, namely first-order hyperbolic problems, and I haven't talked about those at all. And the reason is that the hyperbolic problems of first order really are very different from the other two classes. And in particular, oftentimes, hyperbolic problems of first order are we tend to think of them as conservation laws, and oftentimes they're nonlinear. Almost always they're nonlinear. All the interesting cases are nonlinear. So typical cases for hyperbolic order problems of first order is, for example, the transport of pollutants in the air, or then also things like gas dynamics. So if you think, for example, of how gas flows at very high speeds around an airfoil, then the appropriate description of this would involve, let's say, the conservation of mass, the conservation of momentum, the conservation of energy. And that leads to a hyperbolic system of first order that is nonlinear. In fact, a rather nasty nonlinear equation. But so that's sort of the kind of problems that you should think about when you think of first order hyperbolic problems. And like I say, they're very different. So what I would like to do in this class is introduce you, let's say, to some of the ideas and some of the techniques behind this and what makes it so difficult. I don't really want to go into too much detail with this, because what we talk about in this class is primarily finite element methods, and it turns out that finite element methods are not, let's say, the traditional tool for hyperbolic equations of first order. So historically, at least, people have more used finite volume methods for this, for example. And I'll show you a few of the ideas behind this. I tend to think that, let's say, in the future, finite element methods will have more of a market for these sort of equations, because we have learned over the last 10 or 15 years that many of the finite volume methods actually are just variants of finite element methods, and that the finite element methods give you a systematic way of approaching this problem. So if you understand why finite volume methods work, and you know that finite volume methods are just variants of finite element methods, then you also understand, let's say, how to make finite element methods work. And for finite element methods, you have this much richer toolkit of, for example, producing higher order methods by just increasing the polynomial degree. Anyway, so this lecture is not intended to give you a really in-depth overview of how to deal with hyperbolic problems. This is a whole semester for itself. I just want to give you a little bit of an insight of why it's a difficult problem, and where the difficulties come from, and how you would attack them, for example. All right, so this is a lecture about first-order hyperbolic systems, and the first thing that I would like to do is I would like to get rid of the time derivative. So I told you that the general form of first-order hyperbolic systems looks like this, where you have the time derivative of the solution, and whereas you have the second spatial derivatives of the solution for second-order hyperbolic systems, like the wave equation, for example, for first-order hyperbolic systems, you have first-order derivatives here, and you also have only first-order derivatives here. So this function f really depends only on u, and not on the gradient of u. The system is hyperbolic on certain conditions on the function f that I don't really want to go into. That in itself is a difficult question. When is an equation actually hyperbolic? So let me just assume that you're dealing with one of the typical cases of hyperbolic equations. So the simplest time-dependent equation that you can think of that has this form would be something that we call the time-dependent advection equation, where f of u is really just a vector w times the solution variable u, and then you have initial conditions here, and you would have boundary conditions. One way to write this equation, if this vector field W here. So this W is a function that for every x and every t gives you a vector. If this happens to be divergence free, so if diff W is 0, then you can actually pull this out of the derivative here, and you come up with this equation here that you often see in the literature. This is called the conservative form of the equation. This is called the non-conservative form. As I say, if W is divergence free, they're of course exactly equivalent. Divergence free means in particular it's incompressible. So if this is, for example, a velocity field that you get out of the Stokes equations or the Navier-Stokes equations, then it is divergence free. So you can think of this equation as follows. This W could, for example, be a wind field. So if you think about, let's say, pollutant transport in the air or in water, then W would be at every space point x and at every time t, it would be the direction and velocity of flow with which the medium moves. And U could, for example, be the concentration of a pollutant. So this equation would model how a pollutant that is produced by this right-hand side F is transported along by the wind field. So let's say F would be a point source. If there's a power plant somewhere, W is the ambient wind field, and then U could, for example, be something like the concentration of sulfur dioxide or of nitrous oxide, or these sort of things. So, like I said, I would like to get rid of the time derivative right away. And the way I'm going to do this is I'm going to write this equation in the following way. So I can think of this d over dt plus w dot gradient in the following way. This is really the dot product between 1 times the time derivative plus this whole vector times the spatial derivatives here. That's exactly the same. And so if I reinterpret my, my coordinates as follows, that I say I don't have 1 time and let's say n space coordinates, but in reality I have n plus 1 space coordinates, then I can introduce, let's say, a new vector field W here that has n plus 1 components, and that consists of a 1 plus all of the components that I had previously. And the gradient here is not just the spatial derivatives, but also the temporal derivatives. And so if I just reinterpret what this W and this gradient here stand for, then I can think of this equation up here just as this one here. So I have a problem that looks as if it doesn't have a time derivative because I consider it as a problem in n plus 1 space dimensions instead of 1 time in n space dimensions. This equation has all of the same properties, and that's why I wanted to consider it. So all of the pathologies that you can find for this equation up here, you can already see in this one that is a lot simpler, and the other way around. All of the pathologies that you find in this equation, you will find if you actually want to solve a time-dependent problem. In practice, of course, if you have a time-dependent problem, you're going to solve it using a time-stepping scheme, using the formulation up here. Because it's much easier to solve a time-stepping scheme, let's say, on 2 space dimensions than to solve a 3-dimensional problem, all coupled. But I use this formulation here because I want to introduce you to the, let's say, difficulties of this sort of problem. Okay, so if I have this equation, then I need to pose boundary conditions. And the boundary conditions are now posed in this n plus 1 dimensional space. So these are really the spatial boundary conditions plus the temporal initial conditions. And now, what does that mean? So what kind of boundary conditions can I actually pose? So if you think of this equation, I can think of this as, let's say, pollutant transport by a wind field W that has now a temporal and a spatial component, or you can just think of, let's say, if I were originally solving something, for example, in 2 space in 1 time dimension, then now I have a 3-dimensional wind field. So I'm thinking of this pollutant transport by wind. if you think of this, it's quite clear that, let's say intuitively, you can only pose boundary conditions in those places where something flows into my domain. Okay, so I'm sitting in Central Texas here when I record these lectures. If I had a model that provides me with a wind field over Texas, then where along the boundary of Texas can I pose boundary conditions? Well, only where wind flows into Texas, so let's say from the Gulf of Mexico. Whereas where wind flows out of Texas, let's say into Oklahoma to the north, then I cannot pose boundary conditions for the pollutant concentration in these places because that doesn't make any sense, right? Boundary conditions influence the solution in the interior of the domain, and clearly in places where the wind flows out of my domain, that has what value the concentration would have on the boundary on these points cannot possibly have any effect upstream where the wind came from. So the influence for this sort of equation is transported only along the lines that, let's say, we call these characteristics. These are the lines along which information is transported, and they start at the inflow boundary and make their way through the domain. So I can only impose boundary conditions on the inflow boundary condition, on the inflow part of the boundary, and I'm going to call this part gamma in. So these are all of the points on the boundary for which n dot w is less than 0. That means if w points into, on the boundary, if w points into the domain, then n dot w is a negative number because n is a normal vector that points out, w points in. Okay, so n dot w would be a negative number. This is exactly the part of the boundary that is the inflow. There's a part that is outflow, that would be those points on the boundary for which n dot w is positive, and then there might be places where n dot w equals 0. Those would be the places where my wind field is tangential to the boundary, right? If w is tangential to the boundary, n is the normal vector to it. In that case, n dot w would be 0. In these places too, I cannot impose boundary conditions. Okay, so let's do as we always do. We transform this equation into the weak form. So we start with the conservative formulation. We multiply it with a test function. And then we want to integrate by parts. So we integrate the divergence over here. We get minus the gradient out of this. So minus gradient test function times w times u. And I get a term that lives on the boundary. So I get phi times n dot wu on the boundary. That's what I get by integrating by parts. Now, what I need to do then is I need to split this part of the, or I need to split the boundary into the inflow and the outflow part. Now, on the inflow part, I have posed boundary conditions. So I don't have this on this slide here. On the inflow part of the boundary, I say that u equals g. So that's the concentration that exists on the boundary in those places where something flows in. Okay. So I split this integral over the entire boundary into that part of the boundary that is not inflow, and in that part that is inflow. On the inflow part, I know that u equals g, and so I can bring it over to the right-hand side. And what remains on the left-hand side is only that part that lives on the remainder of the boundary. That's the weak form of this problem. Now, I can use a naive approach, and I can just take this weak formulation of this problem. And as always, I can restrict u to a discrete space. I can use test functions only from this discrete space, so typically a finite element space, such as the Lagrange elements. And then I can write down this discrete weak form and can try to solve it. And that's what worked for the Laplace equation. That's what worked for almost any equation you can think of. So you might think, well, sure, let's do the same thing here. The problem is that it turns out this does not work. This does not work because what actually happens when you do this is that you get a solution that is oscillatory. And to make things worse, these oscillations become larger and larger and larger, the smaller and smaller the mesh becomes. So you get oscillations that become larger, and ultimately you get something that does not converge. Or maybe it converges, but it converges to the wrong solution. Actually, that would not. So it converges to something that is not a solution of the original partial differential equation. And in order to understand why that is so, we actually have to go back to the differential equation itself. So this whole non-convergence thing is a little bit baffling. Actually, before I show you the let's say some of the mathematical reasoning, let me demonstrate this actually in practice. So we have a tutorial program, step 12, that solves the advection equation, this transport problem here, with a discretization that actually works. But it's relatively easy to modify step 12 to use continuous finite elements, the usual finite elements that we always want to use. And like I say, this is something that doesn't work. But I wanted to make this experiment anyway to demonstrate what actually happens. So if I modify step 12 to use a continuous finite element, then on the coarse mesh, I get a solution like this. So what's happening here is we impose boundary conditions on this bottom edge here, and we have a wind field that forms a quarter circle. So our wind field starts in this direction and then turns around and comes out perpendicular out of this left edge. So in every place here, we have transport that goes around in quarter circles here. And the initial conditions are supposed to be 1 here and then 0 over here, which is of course something that we cannot represent with a continuous finite element, so that's why we have this slope here. You'll see a little bit how this better how this initial condition or this boundary condition looks like when I refine the mesh. So let me show you what happens when I do refine the mesh. This is the coarse mesh, and the next mesh looks like this. I have an adaptive mesh. You can go to step 12 and look this up. If I refine one more time, I get something like this. So you start to see there's 1 here, 0 over here. And again, I have transport of these of this, let's say, concentration 1 over here. So it goes out in this direction. My inflow part is here. And the 0 is transported around here. So far, this looks actually quite all right, right? I've made some progress. This is clearly not well resolved. This is better resolved. This looks better. There's a few wiggles here. There's a few wiggles here. But maybe we can still argue that this is only because the mesh is too coarse. Maybe we can say we need to refine the mesh some more. So let me show you what happens when we refine the mesh some more. The next step looks like this. And you see that the interface is sharper. But compared to the previous one, the oscillations at this interface have also become larger. And if I do this one more time, I get something that looks like this. And this is not a bug in my program. This is what happens when you use the standard continuous finite elements for the transport equation. So this is already not very good here, right? I have these spikes here that are very large compared to the height of the jump that I really want to see. And if I do this one more time for a 5th adaptive refinement step, I get something that I can't even plot anymore. So the solution looks like this, and you can easily imagine that if I keep doing this, the oscillations become worse and worse and worse and worse, and it's not going to converge to anything that I'm interested in. So like I said, let us think about the causes for these sort of oscillations. And it turns out that the causes are not actually inherent in the discretization, but that we have to go back to the original equation actually to understand some of this. Namely, it turns out that these hyperbolic equations of first order typically have infinitely many solutions. This is not what I should say. These equations have infinitely many solutions. Many of them are physically, or all of them, with the exception of one, are physically not correct. So when we think of an equation as a description of a physical process, of a natural process, typically what we come up with is equations that have only one solution. Let's say we want to describe a diffusion process. Well, we come up with the Laplace equation, or if it's a time-dependent problem, we come up with the heat equation, and both of these equations have exactly one solution, which happens to be the one that is physically correct. For these hyperbolic equations of first order, it actually turns out that the equation that we have come up with that describes this transport process has infinitely many solutions, only one of which is physically correct. And we can try to think about whether we can come up with a criterion that only one of these many solutions actually satisfies, that picks out of these infinitely many solutions exactly the single one that is physically correct. And the way we describe this is that we say, well, it is the viscosity limit. So we pick out one solution, or we can choose the one solution because it is the only one that is the viscosity limit, or let's say one that satisfies an entropy condition. This is something that is actually relatively new. So the way to pick out the one physical solution is something that we've known only, I don't know, maybe since the 50s. Whereas, of course, for problems like the Laplace equation, that's the 1950s. For the Laplace equation, for the heat equation, these sort of things have been known certainly since the beginning of the 20th century, since we know things like Hilbert spaces, Lebesgue spaces. So once you figure out that the solution of the Laplace equation should be in H1, you immediately have uniqueness of the solution. Right? So this took a lot longer for people to figure out how exactly to describe these sort of problems for hyperbolic problems of first order. And that sort of illustrates already why this is difficult. So let me give you an example of an equation that is hyperbolic and that has infinitely many solutions. And we're going to take a look at it and see if we can sort of identify the characteristics of what the physically correct solution should be. So an equation of a hyperbolic problem would be something that we call the Eikonal equation. The Eikonal equation is we're looking for a function of one argument, so u of x, so that the magnitude of u prime of x equals 1. In other words, that u prime should be plus or minus 1. And we want it to be so that the function at the left end and at the right end equals 0. Okay? We tend to think of this as a function that we call the distance function from the boundary, because this function, if the gradient is 1 or if the derivative is 1, it grows, for example, with unit speed as we go away from the boundary. At the boundary, the value is 0, because the distance at the boundary, the distance to the boundary is 0, and then this u grows with unit speed as we move away from the boundary. So here is one solution to this problem, right? At the left and at the right endpoint, the function u is 0. The slope is plus 1 here, minus 1 here, so the magnitude of the derivative is always 1. Okay, that is clearly a solution. We cannot hope for it to be a strong solution, so in this particular case, there is, of course, a point where the derivative does not exist, so it's at best a weak solution of this problem, but it is a solution of this problem. It's relatively easy to see that there cannot be a strong solution, so if you hope for a function that is differentiable everywhere, then you cannot have a... so if the function would be continuously differentiable everywhere, then u prime would have been equal to either plus 1 or minus 1 everywhere. It cannot jump, because otherwise it would not be continuously differentiable, right? So if u prime is equal to plus 1, then you cannot start at u of 0 equals 0 and end up at u of 1 equals 0, right? You would have a function that grows linearly, or if you choose the negative sign here, you would have a function that decays linearly, but it cannot satisfy both of these boundary conditions at once. So it's easy to see that there cannot be a strong solution to this problem, but this the one that I showed you, is clearly a weak solution. It satisfies the equality absolute value of u prime equals 1 almost everywhere. And so if you multiply it with a test function that is smooth enough, let's say continuous, for example, then the equality is satisfied. Okay? So I've shown you one solution here, but now let me show you other solutions as well to this problem. So here's another solution that has slope equals to plus or minus 1 everywhere. So the magnitude of the slope is 1 everywhere. Here is yet another one. Okay? And it's relatively easy to see through this process that essentially any zigzag curve that has slope either plus or minus 1 and starts at 0 and ends at 0 is a solution to the Eichhorn equation. Okay, so I have identified infinitely many solutions through this process that all satisfy the weak form of the Eichhorn equation. And that's sort of a problem, right? Because now we have infinitely many solutions, and the question is, well, which one do we actually want to have? So the one that we really that we think we should get is this one here. This is what we tend to think, let's say, intuitively as the solution of the Eichhorn equation, and in fact it is the one that we call the distance function, right? It is 0 here. It grows to 1/2 at the midpoint, because the midpoint is 1/2, has a distance of 1/2 to the boundary, and then as you move further to the right, then of course the distance to the left boundary keeps increasing, but the distance to any of the boundaries decreases as we finally get to the point here on the right. So this is sort of the function that we care about, whereas these ones here are all weak solutions to the equation, but ones that we do not care about. And so when I showed you these pictures of the solution here, for example, you can imagine that maybe what we converge to is one of these other solutions of the transport equation that, well, satisfies the weak form, but is not the physical one, right? So in order to make sense of this problem here, that these sort of things don't converge, we have to figure out what it really is that we call the physical solution, because there are multiple solutions. So in the case of the Eichhorn equation, like I said, the physical solution we probably care about is the one at the bottom left. And how do we describe this? Well, from a physical perspective, when we talk about conservation laws, we tend to think of these sort of things, let's say, in terms of gas dynamics. And in gas dynamics, we know that we have an additional quantity that we call the entropy. And the entropy is something that we know must always increase. That's the second law of thermodynamics. Now it turns out that the increase of entropy is not something that I can derive from the equations of gas dynamics. Let's say if I write down the Euler equations of gas dynamics, then they describe how energy is conserved, how mass is conserved, and how momentum is conserved. These three sets of equations do not have any statement about the entropy. The fact that the entropy must increase is something that I have to impose in addition. So there are infinitely many functions that satisfy the Euler equations of gas dynamics, but only one out of these infinitely many functions actually satisfy the entropy increase condition. So physically speaking, the one out of these infinitely many solutions that I find for these equations is, or only one out of these infinitely many satisfies the physical entropy condition. In physics, the entropy conditions are often called the Rankine-Hugoniot conditions as well. And one of the things that I can show, maybe not I, but some people can show, is that these entropy solutions, so these are the entropy solution is the single one that satisfies the entropy condition, that the entropy solution is also something that I can derive as the viscosity limit. So what I want to do is that I want to put the entropy condition somehow into the original equation. Like I said, if I just look at the equation, it has infinitely many solutions, but only one out of these actually satisfies the entropy condition. What I would like to do, let's say from a numerical viewpoint or from a mathematical viewpoint, is I would like to modify my equation in such a way that it produces only one solution, and that this one solution actually turns out to be the physically correct one. So this is what I call the viscosity limit, and let me show you how to do this. So if I start with the Eikonal equation up here, the Eikonal equation was that the absolute value of u prime equals 1. What I'm going to do is I'm going to add a little bit of diffusion. So I'm going to add an epsilon times minus Laplace of the solution. Okay. This equation is, strictly speaking, elliptic, because it has the second derivatives here. And as an elliptic equation, I can show that for any finite epsilon, it has exactly one unique equation, one unique solution. Okay. This one unique solution I'm going to call u epsilon. And of course, u epsilon is not a solution to this equation up here for any finite epsilon. Okay. But I can ask the question, well, if I let epsilon go to 0, what's going to happen? And it turns out that if I let epsilon go to 0, then the solution u epsilon here will converge to a u, let me call this u star. And this u star actually is a solution of this equation up here. This is something that is not immediately obvious, that it should be like this. Okay? But I can show that if I let epsilon go to 0, then the solution of this set of equations converges to something that is a solution of this thing up here. And furthermore, lo and behold, the limit, and I call this the limit of these u epsilon, I call this the viscosity solution. So not only is it unique, but it also satisfies the physical entropy conditions that I want to pose up here. Okay, this is something that is often called the a theorem, when in reality it's a whole set of theorems that were derived by many of the big people in hyperbolic conservation laws, like Lux and Olenek and Khrushchev and Godunov, over a span of maybe 20 years, that people have figured out that the unique viscosity solution is in fact the physically correct one out of the infinitely many solutions of this equation up here. Okay? So this is this is a deep result. This is not trivial to show this. But it gives us a little bit of an approach how we can solve these sort of problems. Namely, when we say we have this transport equation, for example, and we see that we have all of these oscillations, then we see that one of the problems might be, or one of the solution approaches might be, that instead of discretizing the original transport equation, we should discretize a variant of these transport equations where we add a little bit of viscosity. Okay, so let's say we add minus epsilon Laplace u, and we should choose this epsilon in such a way that, for example, as we make the mesh finer and finer and finer, we let epsilon become smaller and smaller and smaller. Right? So we would say that as long as the mesh is coarse, we can introduce an error, because we know that there's a discretization error. It doesn't matter if we also add an additional source of errors by modifying our equation. But as our mesh size becomes smaller and smaller and smaller, we also want to make this additional term in the equation smaller and smaller and smaller. So then we can hope that our finite element solution approximates not the solution of the original equation, but of this what we call regularized version of the equation, where we have added the Laplacian term to it. And then as we let epsilon and h go to 0, that we converge, in fact, to the viscosity limit. Okay, so that's sort of the general approach that we want to pursue. And so in the next few minutes, what I'm going to show you is how you formalize this in, let's say, a finite element or in a discrete scheme. So before we do this, I should point out the following thing. So when we have this equation here, right, we get a solution u epsilon, and if we discretize this, then we get a finite element solution. Now we know that these u epsilons actually converges to the viscosity solution, to the physically correct solution of the original hyperbolic problem here. If we discretize this, then we get a discrete solution, let's say u h comma epsilon, that depends on this mesh size and on the size of epsilon. And if I let h and epsilon go to 0, it will converge against something in some sense. Of course, it would be nice if it also converged to the viscosity solution. Oftentimes, we can show that it actually does. And in that case, of course, we're happy, because then we have a discretization that yields a solution that actually converges to the physically correct solution. And in particular, it should not have these sort of oscillations. In practice, this is something that is often very difficult to prove. So for some simpler schemes, for the ones that I can show you, it's possible to prove this. For highly nonlinear conservation laws, it's not trivial to do this, and oftentimes it's not known. In that case, we have to more rely on our experience, for example, whether we can expect that it actually converges. But so I just want to point this out. I'm not going to show you proofs. I just want to point out that it's not an obvious question whether the discrete solution of the regularized problem will actually converge to the continuous solution of the non-regularized problem, to the physically correct one. Okay. All right. So let me come back to how we do this numerically then. Basically, there are two, let's say, approaches to solving these hyperbolic problems that have infinitely many solutions. Namely, the first approach is that we use a standard discretization for a modified problem. So let's say we add this explicit diffusion term, and then we can use, for example, a Q1 finite element, and we can see what happens if we let h go to 0 and epsilon go to 0. There are two, let's say, ways to add this, to modify the equation by adding some viscosity, or by adding some diffusion to it. Viscosity and diffusion is the same thing, I should say. So diffusion is what we mathematicians call it. Viscosity is what a physicist would call it, right? But the result is the same. So there are two standard approaches to this. There are many other methods as well that I'm not going to talk about it, but let's say there are two standard approaches to adding artificial diffusion to the equation. One is called artificial viscosity. The other one is somewhat clumsily called streamline upwind Petrov-Galerkin, and because nobody wants to pronounce this, we always say SUPG. And then there are other methods that use the original kind of equations, but that use specialized numerical schemes. So for example, finite volumes and discontinuous Galerkin methods fall in this category. Now, if you look at all of these methods carefully, all of them somehow add some diffusion. So they, whether explicitly or implicitly, they always add some kind of diffusion. And the hope is, of course, that they approximate the viscosity solution. That's the physically correct one. So let us take a look at how to do this in practice. So we start with the simplest case again with the transport equation. So I'm given a wind field W, and I'm looking for a function u that satisfies diff WU equals 0 and equals to g on the boundary. And I wanted to solve this with a regularized version where I add a little bit of this diffusion here with a factor nu that corresponds to the epsilon before. And I'm going to choose this nu in the following way. So it's a spatially dependent function that I choose as follows. So it's going to be a non-dimensional constant beta times the norm of the vector field W, so the norm at every given location, not the, let's say, not the capital L2 or the H1 norm, but the magnitude of W, times, for example, the mesh size h of x. So in places where h is small, my artificial viscosity is going to be small. And in places where the mesh is coarse and h is large, the artificial viscosity will also have to be large. Okay? So One of the things that is not very difficult to show is that if beta is large enough, then this yields a discretization that is stable. So I can use, for example, the typical Q1 elements for this, and I will find that the oscillations do not grow. As a matter of fact, they will become smaller and smaller, and the solution will converge to something that looks like what I want to do. It imitates the viscosity limit, or the artificial diffusion limit, because as h goes to 0, so if I make my mesh size finer and finer and finer and hope to approximate the exact solution better and better and better, the artificial viscosity also goes to 0. So that's exactly the sort of setup that we had here, right? That I add something here, that I get a solution for every epsilon, and that I let epsilon go to 0. Well, here I let epsilon go to 0 because I let h go to 0. If I make my mesh finer and finer and finer, hopefully this will yield the viscosity limit. Okay. I should say it only imitates the viscosity limit, and it is in fact a difficult problem to prove that it converges to the viscosity limit. But let's say the setup of our method works that way, that it imitates it. Here's a slightly better choice. So it turns out that we don't really need to have artificial viscosity in all of those places where the solution is smooth. If you look at this carefully enough, you will find that oscillations really only happen in those places where the solution has, for example, a discontinuity. And the realization that you come to then is that you should only choose this new large in those places where the solution actually has a jump. Whereas in those places where the solution is smooth and continuous, we don't really need the viscosity to be large. And so there is a modification that's relatively recent, and that's been propagated primarily by my colleague Jean-Luc Gamond here at Texas A&M, that looks essentially like this. So we start with this thing up here, but then we multiply it with the minimum of 1 and a local magnitude of a residual divided by some normalization constant. And the idea goes like this, that if the solution has a jump, then the residual is large. That's sort of an empirical observation. So if the solution has a jump, the residual is large, then this term is large here. And the minimum of 1 and large will be 1. So in that case, I get back the nu that we had before. So our artificial viscosity is exactly what it was before. On the other hand, in places where the solution is smooth, the residual is going to be small. And so if the residual is small, then the minimum of 1 and small is small, and I get an artificial viscosity nu that is in fact typically much smaller than this thing here. So what that means is that in places where the solution is small, I only very slightly perturb my original equation. And instead of adding this heavy-handed diffusion, I add the diffusion only in those places where something is actually going on, right? Where there's jumps, where there's discontinuities, where there's large gradients, and so on and so forth. Whereas in those places where the solution is small, I essentially leave the original equation unperturbed. So we use this sort of scheme in step 31, step 32, and step 43 if you want to look at this. This is the artificial viscosity, artificial diffusion approach, and the alternative to this would be something that is called streamline upwind Petrov-Galerkin, SUPG. And essentially the way this works is that instead of multiplying this with a test function phi, you would multiply it not with phi, but with a test function from a different space than what you use for the trial functions. Namely, instead of multiplying with phi, you multiply it with phi plus tau times the divergence of w times phi. Okay, so this is the new term here. Then we do integration by parts, as we always do, and this tau here then takes on the role of the artificial viscosity that we had before, and so we let tau go to 0 as h goes to 0. And it turns out that this particular approach, that's called Petrov-Galerkin because we use different test than trial functions, that this also yields a stable discretization. And I want to reinterpret this a little bit for you to show you, let's say, the connection to the scheme that I showed you previously. Namely, if you think of this as follows. So what I can do is I write this as phi times diff w u plus tau diff w phi times diff w u. Okay, and then I can integrate this by parts, and I can separate out the phi so that I get phi times the strong form of the equation. And so if you do this integration by parts from here to over here, what you will find is that the strong form of this equation here is in fact diff wu, that's the original term. And then in the artificial viscosity method, we added minus Laplace epsilon u here. Well, here, the strong form actually adds minus tau w dot gradient diff wu. And I can reformulate this if this w is a divergence-free vector field in the following way. Namely, this is minus tau divergence w cross w, so that's the outer product, gradient u. Now, if it wasn't for this factor in here, if this was the identity matrix, so this is a d by d matrix, okay? If I wasn't for this factor here, I would have divergence gradient, that's exactly the Laplace operator. Okay, and I would have the artificial viscosity formulation. What I have here is not what we call isotropic diffusion. So if I add Laplace u to the equation, then that corresponds to a process where I allow diffusion in every direction. Here, I actually only allow diffusion in the direction of w. So if you think a little bit about what this means, then that means that there is diffusion only in the direction of w. So it's a one-dimensional diffusion process. And so this is sort of a slightly refined version of the isotropic artificial diffusion that I had on the previous slides, where I really allow diffusion only in a subset of directions. And it turns out that that is enough, that I get a stable solution through this process as well. So this streamlined diffusion process is enough to yield a stable solution. If I want to compare these two methods with each other, the SUPG really only adds viscosity in certain directions. It turns out that SUPG is rather difficult to generalize for time-dependent cases. So if I don't just look at the stationary transport equation, but if I want to go back to the case where I have du over dt plus this term here, it turns out that SUPG is something that's very difficult to get right. Artificial viscosity, the approach that I showed you before, is indiscriminate in this regard. It uses diffusion in every direction, but it can be made to work for the time-dependent case as well. Okay? Both of these methods require tuning of a dimensionless parameter. So in one case, it's the beta, and in the SUPG case, I need to make tau depend on the mesh size as well. So there's another scheme for this where I have a similar coefficient that is dimensionless, but I need to tune it. So a typical number, for example, for beta in the artificial diffusion case would be somewhere between 0.1 and 1. But I need to figure out, I need to play with this. Beta needs to be large enough so that the scheme is stable, but small enough that I don't introduce too much error due to this approximation. Okay? Both of these methods generalize rather easily to higher order methods. So whether you use Q1 elements or Q2 elements, it's not very difficult to make them to work for higher order elements as well. All right, so this was how you approach this if you really want to use a finite element method. The alternatives to this are things like, for example, finite volumes that use the original equation but use a completely different approach, and discontinuous Galerkin methods. And so here's, let me introduce you really quickly to what finite volumes do or how they approach this. So finite volume schemes start with the same domain as we had before, and they subdivide this domain into individual cells. And for finite elements, we typically choose either triangles or quadrilaterals in 2D, and tetrahedra and hexahedra in 3D. For finite volumes, this is not actually necessary. Finite volumes can use any kind of subdivision. So for example, over here, you see something that is called a Voronoi subdivision, or Voronoi cells. So this cell here, for example, has 1, 2, 3, 4, 5, 6 vertices. And there are probably others that have 5 and 7 and any number. It doesn't really matter. All you need to do is you need to subdivide your domain into any kind of set of cells. And then you start with the strong form of the equation, and instead of multiplying it with a test function, what you're going to do is you integrate it over a single cell. Okay, so if I have a cell K, I'm going to integrate this equation on the left and on the right over K, and of course my solution function U still has to satisfy that the left-hand side and the right-hand side are equal on every cell. Now, one of the things that you can do in this sort of case is that you have an integral of the divergence of something. And you remember the divergence theorem, namely that if I do this, that the integral of the divergence of this thing equals the integral of the normal vector times the integrand W times U. Okay? That's essentially just integration by parts. You can think of this as, well, I have a 1 here, and I want to bring this divergence over the gradient of 1 is 0, so the domain integral disappears, and all that remains is the boundary integral that comes out of the integration by parts. So this is sort of the fundamental form that I have in finite volumes, and let me give you an interpretation. So I'm integrating over the boundary of a cell. What do I integrate? Well, W is my wind field, U is a concentration, so W times U is a flux in direction W. N dot W times U is going to be the flux in the direction normal to the cell. And so what this says is that if I integrate the flux over the entire boundary of a cell, the normal flux over the entire boundary of the cell, then this equals the production of pollution, F, on this cell. Okay. In other words, if F is 0, so if I am in some pristine part of Texas countryside where there's no power plant and no production of pollution, and I cut out a cell and I integrate the normal flux around the entire cell, then the result must be 0. What this means is that in this cell, whatever flows in must go out. Okay? So that's sort of the intuitive interpretation of this, that the sum of what goes in and what goes out must equal 0. That's what this equation does. Or if you do have a right-hand side, then the sum of what goes in and what goes out must equal the amount that was produced locally. So this is going to be the basis for finite volumes. Now, if I use this sort of form, then what I'm going to do is I'm going to sum this up over all of the cells. Okay, so I'm going to write a sum over all the cells here. And then what you get is, well, a sum over all of the cells over the boundaries of each cell. That gives me 2 terms for every interior interface, namely when I come to this boundary between 2 cells from one cell, plus when I come from the other side. And I can write this as follows. So this gives me a sum over all of the interior edges, where I have n dot W times the jump of U. That's like the value of U in one cell minus the value in the neighboring cell, plus a sum over all of the exterior edges. And there I get just 1 term each. That is the difference between the boundary values and U. So this is the basic formulation for finite volumes, and then what I'm going to do is let me assume that the solution is constant on every cell, then this jump here is going to be the value in this cell minus the value of the neighboring cell, and essentially this gives me a linear system that relates the values here on every cell to the values on the neighboring cells. In much the same way as, let's say, in finite elements, it gives me a system that connects the values at every node with the neighboring nodes. Okay. Here I'm thinking of the concentrations in one cell. I assume that's my numerical approximation that in every cell the concentration is constant, and is going to give me a relationship of the concentration here with the concentration in the neighboring cell to the left and to the right and all around. Okay, that's sort of the idea of finite volumes. Finite volume schemes, let me summarize this part. Finite volume schemes have been shown to be exceptionally stable. They can solve problems that have discontinuities that are very nonlinear. So they don't produce, let's say in the typical versions at least, they don't produce these highly oscillatory schemes. They're very flexible with regard to cell shapes. They can be arbitrary polygons. The problem is that in their lowest order versions, they're not very accurately and frequently very diffusive. So if you look at the solutions, oftentimes where there should be a shock, a discontinuity, it turns out that it's actually very smoothed out. Now, in the finite element method, what we typically do is when we have these sort of problems that something is smoothed out, we just introduce higher order polynomials because we know that they're better able to approximate discontinuities. And that is the one big downside of finite volume schemes, that they're exceptionally difficult to generalize to higher order methods. Because our whole setup was based on the premise that on every cell, we assume that the concentration is constant. If we assume that, for example, on every cell the concentration is a linear profile, then computing these jump terms along the interfaces that relate the values here and on the neighboring cell becomes much more difficult. And primarily the difficulty is that if we do this, that we end up with schemes where we reintroduce oscillations. So we have to come up with all sorts of approaches again to limit these oscillations. And so in finite volume schemes, if you ever hear these terms, these additional modifications that make the oscillations go away are often called flux limiters or slope limiters. What it boils down to is that it's exceptionally difficult to get higher order finite volume methods that have the same stability properties. That's the downside of finite volumes. They're very good, very stable if you use the lowest order methods. They're not easy to generalize. So what I want to talk to you about in the rest of this lecture is an alternative approach to finite volumes that we call discontinuous Galerkin methods. Discontinuous Galerkin methods is something that people have come up with, let's say, they date back to the 70s, but I think the real power has only been understood in the 1990s. When people realized suddenly that we can introduce a particular way of dealing with finite elements where the shape functions that we use are not continuous anymore. But let's say we allow functions that are discontinuous from one cell to the next. And what people realized in the context of hyperbolic equations is that the lowest order finite element methods with these discontinuous shape functions happen to be almost exactly equal to the typical finite volume schemes. And so there was a big push in the 90s and 2000s to analyze these schemes because we know very well how to make finite element methods higher order, right? We just increase the polynomial degree. And so what people have started to do then was to rewrite or to reinterpret finite volume methods as discontinuous Galerkin methods and use that as a template to produce higher order methods. So that is why in some of the other lectures I have mentioned that to me finite volumes or also finite differences is really only a variant of finite elements, because oftentimes we can find that the lowest order finite element method is equivalent to, for example, the typical finite volume method or to a simple finite difference method. And so what I would like to do is give you just a very basic introduction to what these discontinuous Galerkin methods do in the next 5 or so minutes. So you start again with the conservative formulation diff(W) times U equals F, and you multiply it with a test function, so you get this weak formulation. We know that this was not stable if we used continuous finite elements. Now, we can modify this whole approach by allowing ourselves discontinuous functions. So we allow U to be a function that is discontinuous between cells, and then we also allow this phi to be discontinuous between cells. So it's not a function in H1 anymore, for example, but it is discontinuous. And of course, when we want to integrate by parts, now we have to pay a little bit attention, because I would get the gradient of phi, and the gradient of phi would be difficult because phi is not a continuous function anymore. So I have to be careful. But what I can do, if phi is piecewise smooth, then I can do this integration by parts cell by cell. What I come out with, if I do this cell by cell integration by parts, is a sum over all cells, where I have integrated on every cell, and I get something like this. I can do the same kind of trick that I did for finite volumes, namely that I can rearrange the edge terms. And I come out with something like this, where I have a sum of cell terms and a sum of terms where I have to jump between cells on the interfaces between cells. Then I have to deal a little bit more with the question why I'm integrating over the boundary of this function phi, but phi is actually discontinuous. So there's a number of technicalities that go with this. Ultimately, what it boils down to is this. So if I do this, if I derive this appropriately, then I find that the lowest order DG methods are often equal to the lowest order finite volume method. It's a very convenient way to analyze finite volumes, and it's a systematic way of producing schemes of higher order. So I don't want to go into more detail with this. There's a whole literature out this, and I must admit that I'm not an expert on this either, but I hope you have gotten a little bit of an idea of how to think about hyperbolic problems, what the problems there are, why we need to think about this on a continuous level. And I hope I've given you a few of the ideas of how you would actually solve these sort of things in practice. As I say, I don't want to go into more detail. There are other people who know a lot more about this, and there's a vast amount of literature. All I wanted to give you is, let's say, the basic ideas of this. And I think with this, I'll leave it for hyperbolic problems, and we'll come back to problems that are more amenable to finite element methods in the remaining lectures.